Okay, so this is the summary, right? The size of the L2 cache should be much larger so that, typically because people use inclusion, okay, where all data which is in L1 is also present in L2. Therefore, your size of L2 cache should be much larger than L1. Obviously, higher associativity at the level 2 cache and lower at the level 1 cache, so that you have better hit time at L1 cache and less miss rate at level 2 cache. Okay. Block size, if you have your non-uniform block sizes across the levels, then replacement becomes a problem, especially if you have inclusion, right? Because when you replace a block in L2, you will have to replace the corresponding blocks in L1. Okay, so if you have a block size of 128 bytes in L2 and 64 bytes in L1, then if you replace a block in L2, you will have to replace 2 blocks in L1. Okay, so this sort of complex logic will be needed if non-uniform block sizes are present in the different levels of the cache hierarchy. But on the other hand, if you look at it, larger block sizes lead to less miss rates. And because your L2 cache size is larger, a larger block size makes sense. So it's a question of balancing across these two issues, right? So Pentium uses non-uniform block sizes, looks like, where they use a larger block size in L2 and smaller block size in L1. So, and then in multi-level inclusion, if you have, if you don't say that it must be there or it must not be there, then you have more complex logic whenever there are dirty blocks replaced in L1 cache, right? So typically the caches use mutually inclusive, meaning that if there are blocks in L1, they must be present in L2. That's the general choice made to keep logic simple. Okay. So let's come to the next thing. In fact, I thought I'll finish all of the cache optimizations today, but anyway, I unless you people participate, it'll become slow, but slow without making much progress, right? Because I don't like to make progress by talking all the time. You're doing enough of passive learning by looking at videos. I don't think you should have too much of passive learning. That's not the most effective learning at all, anyway. Okay, so let's look at this situation when a read miss occurs, okay, in a write-through cache. What do? Write-through cache. So, whenever there is a read miss, what we are saying is there is a block in the cache and you are hitting that block and you find that the tag does not match. So it's a read miss because of that, right? Now that's a dirty block, okay? Where it is a write-through cache, which is using a write buffer. Okay, so it's like this. Let's be very clear about the scenario. I have written to that block, okay? And it's a write-through cache and which is using a write buffer. So what will happen? I'll write to the cache, but I'll also write that word to the write buffer. Okay, so that the write buffer will continue to write to the main memory in the background. Okay, now I issue a read. The write has not completed, right? The write has only completed to the cache, and to the write buffer. It has not completed to the main memory. At this point, this processor issues a read, which falls in the same block, and it is a conflict. So you have to replace that block. What do? That is the question. Obviously, you would like the write to the main memory to be finished before you replace the block. Okay. So, which will basically increase the miss penalty, because now you have not only the number of cycles needed to access the main memory to read the data, but you also need the memory cycles to write the data and then memory cycles to read the data. So your miss penalty can be almost doubled. Okay. How do you reduce this? One way of reducing it is check whether whatever updated value, because the read miss can also be that it's in the write buffer. Okay, you have issued a read to some, so you have not finished writing, you replace the block and again hit a read miss for the same data that you were looking, you were writing to the main memory. So the data may be updated, data may be in the write buffer. It may not have yet updated the main memory. So the complicated logic would be to check the write buffer. If the updated value is in the write buffer, not yet in the main memory, you take the data from the write buffer and use it in the processor, even while, in the background, it writes from the write buffer to the main memory. Okay. So this is one way of reducing miss penalty. So from almost double the main memory miss penalty, you are bringing it down to the miss penalty of the write buffer. Okay, so you reduce the miss penalty significantly, but at the cost of much more complicated logic. Any questions on that? Okay, the second thing is when you are using a write back cache and you are basically, a read miss occurs to a dirty block, which means that you have to replace the dirty block. So again, the same situation, you replace the dirty block, bring in the new block, and then, basically process the, read request from the processor, right? That will be quite costly because you have to replace the dirty block, bring in the block that you want to read. So it's again twice the main memory penalty that you are looking at. Another method of doing it is write the dirty block into the write buffer, bring in the read block, issue the read to the processor, and let the write happen in the background from the write buffer into the main memory. By this, you will reduce your miss penalty to only one access to the main memory before the read is actually issued to the processor. So that is, one way of reducing miss penalty. Any questions on this? Because, if you have any questions, please ask. I think we have another half an hour. So the last optimization is left to cover, but I just want to make sure you understood this. Okay, since there are no questions, I'll go to the last optimization, which is the only optimization here about reducing the hit time. Please note that when we were discussing optimizations, we said we can optimize by reducing any of the three parameters of the average memory access time, right? We can reduce the hit time, we can reduce the miss rate, we can reduce the miss penalty. We saw three methods by which we can reduce miss rate. One is increase the block size. increase the cache size, and increase associativity, right? Then we looked at two methods to reduce the miss penalty. One is multi-level caches, and the second one is basically giving priority to read accesses than write accesses. So whenever there is a write that is, triggered by a read miss, we will actually process the write after we finish processing the read, so that the read can proceed while in the background we can proceed with the write. So that reduces the miss penalty for the read miss in the case of a dirty block. Now we come to the only optimization in this set of optimizations which reduces the hit time. When we go to the next chapter, we'll see a few more optimizations which reduce the hit time, miss rate, and miss penalty. But in this case, this is the only one which we are going to look at for reducing hit time. Now, what are the steps to access the caches? Now, cache addresses are physical addresses, okay? So therefore, basically when you talk about access from the processor to the memory, the processor gives you virtual address, right? The processor actually puts out the virtual address, which goes to the MMU, the memory management unit, which you studied about, I hope, in your COA class, right? And the memory management unit translates it from the virtual address to the physical address, and you know how to translate it. And then puts the physical address on the address lines to the main memory or the cache. Okay. So the physical address is what we are using to access main memory or cache. Now you can speed up this translation from virtual to physical address by using the TLP, which is the cache for the page table. We had discussed this a few classes back. Then after you translate from virtual address to physical address using TLP, use the physical address to look up the cache. If there is a TLP miss, then your cost is going to be very high, because you have to go to the main memory to look up the page table, then do the virtual address to physical address mapping, and then you put the physical address, and if there is a cache miss, then you go again to the main memory, fetch the block, then you do the read from the cache. It's a long process. The hit time is going to be very large. Even if there is no miss in the cache, but there is a miss in TLP, then there will be a problem. Okay, the hit time will be badly affected because you have to look up the page table. Now, even if you have the TLP, let us say that the hit time for your cache is 1 cycle. Similarly, let us say that the hit time for a TLP is also 1 cycle, and therefore let's assume that in 1 cycle or at most 2 cycles, it will actually translate the virtual address into physical address. Still, instead of having 1 cycle as your hit time to look up the level 1 cache, you are now going to have 2 cycles to look up the cache. 1 cycle to translate the virtual address to physical address by looking up the TLP. Another cycle to read from the cache. So it will actually, reduce the speed of the processor, because every time you need to look up the TLP, the processor has to stop and wait. And then when the cache is looked up and the data is provided, the processor can proceed. So for every instruction or data access, the processor will stall 1 clock cycle if we do this way. This is a problem. So what do we do? One solution would be that instead of having physical addresses to access the caches, have virtual addresses to access the cache, what are called as virtual caches. So you don't translate the processor puts out the virtual address. You use the virtual address to index into the cache and also do the tag comparison. But only if you go to main memory, you do the translation to the physical address. This is one solution to the extra cycle that you need to translate from virtual address to physical address. But if you use virtual addresses, we have a lot of problems that can happen. One is that please remember that you have what are called as page protection bits in your TLB and page table, right? Which tells you whether that page has an access to read, write, or execute. And if you are trying to access that page with the wrong permission, then you are actually kicked out. That is not going to be present in the cache, right? So, your protection checking is not done. One solution to this would be to copy the protection bits to the cache entries, which means that you're increasing the number of bits per entry in the cache. So increase the power consumption of the cache because of that. That is one solution. But another problem is that there is some concept of aliasing. I talked about this earlier when we were talking about instruction set principles, but let me again reiterate. It is basically two different variables actually referring to the same location, right? Like the variable and the pointer to the variable. So when you dereference the pointer, you're pointing to the same physical memory location. This is an alias, and such aliases will have different virtual addresses. But when you translate to physical address, they will map to the same physical address. Now, if you use the virtual addresses to index into the cache, these may actually be in two different locations in the cache. Okay, what will happen? If you update the value using one virtual address, the other virtual address will be having still the old value. This will not happen with physical addressing because both these virtual addresses will map to the same physical address. Therefore, only one entry will be in the cache. When you update that entry, it's reflected for the other virtual address also. But if you are using virtual caches, the two virtual addresses will be in two different locations in the cache and therefore may have mismatched values. Okay. Any questions on that? If somebody is not clear. I can also give the example of shared pages. Sir must have talked about shared memory, how it's implemented, is it not? Can somebody tell me how shared memory is implemented in OS? Yeah. How is shared memory implemented? The virtual addresses are not going to be the same in both processes, right? However, the page tables of the two processes will map the two virtual addresses to the same physical address. Okay. And therefore, you get those pages mapped into the process address space of each of the processes. Okay. That's another case of aliasing, if you want to call it aliasing. Okay. It's basically shared memory. Obviously, the virtual address will be different in the two processes, but the page table will map them to the same page so that they can share the page between the two processes. So such situations are all messed up royally when you use virtual caches because you are using virtual addresses to index into the cache. Now, whenever you do a context switch, okay, so whenever you do a context switch, what happens to the cache when you use virtual addresses is the question. Now, virtual addresses of different processes are the same. Do you agree that every process has a virtual address from 0 to some value, depending on the size of the executable? So they'll have duplicate virtual addresses, even though the physical addresses can never be duplicate unless they are doing a shared page. the physical addresses of two processes can never be the same. In fact, the operating system will kick you out if you try to access the address space of another process, right? You get a segmentation fault. So, but virtual addresses will be duplicate addresses in every process, because you start your virtual addresses with 0 and proceed until the executable file size at least. So if you are using virtual caches, that is caches which are addressed by the virtual addresses, then every time there is a context switch, you have to flush the cache. If you don't, the virtual address which is present in the cache, it is marked valid. Remember that when the previous process was using it. So this process will come, use the same virtual address and look at the wrong information, because it's not its information that the cache is having. So you'll have to invalidate all the entries in the cache to prevent such mess from happening. So it leads to more costly context switch when you move from one process to another if you are using virtual caches. Then the fourth point is that IO devices use physical addresses for the DMA. They don't use virtual addresses. So if you want to have DMA into cache, then you have to do a lot of gimmicks to make IO happen into the cache directly. So these are the various problems that you hit if you use virtual addresses to index the caches. But what is the gain? The gain is that you avoid the address translation, so your hit time will be only one clock cycle. So to try to solve one problem, we are hitting many other problems. So what's the solution is what we have to look at. But before we proceed, there any questions on any of these points? I'm assuming you know your context switch well and so on. If you are not clear, you have doubts, you're not sure why I'm saying something, then I can answer the questions. Of course, the context switch here, like it said, you can also add the PID bits to the cache, right? So whenever you're accessing the cache with the virtual address, you also compare the PID of the process that is issuing this address with the PID of the entry in the cache. So it's, the PID bits, you can think of them as part of the tag match. Okay. Please note that TLB also has the same situation. I'm sure you read in OS. Did you not? Because even in TLB, the entries will have to be flushed when you do a context switch unless you have the PID in the TLB. So the PID bits here can be thought of as extra bits in the tag comparison. But every bit you add to the cache obviously adds to the cost and power consumption. Okay, and also the complexity of the match. So it can still affect the hit time. Okay. So if no questions, we'll consider what is the solution. What they have is what is called as virtually indexed, physically tagged cache. What do? Please remember that the address, the virtual address, consists of the page number and the page offset. So you use only the page offset bits for both the index and block offset of the cache, and the remaining bits, which is basically the page number bits, as the tag of the cache. Now, what is the advantage of doing this? Offset bits, please note, are the same whether you're talking about virtual address or physical address, right? It's only the page number which gets translated into the frame number. And then you basically take the start frame address and add the offset to get to the exact memory location that you are trying to access, right? So that's basically how translation happens. So you use the page number as the tag and the offset as the index and block offset fields of your cache address. Now, therefore, you don't have to translate the offset. Do you agree? There is nothing called translate because the exact same value comes to you in the physical address also. So what do you do here? You do the translation from the page number to the frame number in parallel with, indexing into the cache using the offset index bits, and then reading the particular block byte of the block or word of the block using the block offset bits. So you are doing the translation using TLB. At the same time, what you are doing, you are taking the offset bits and issuing the indexing into the cache and using the offset to read the particular word that you want. By that time you finish reading from the cache, your translation from virtual to physical address is completed, at which point you do the tag comparison and you are done. So there is a parallel activity that you are doing, because of which your hit time is reduced. Now, the advantage is that you are basically using the virtual address itself in some sense to index into the cache, but you are having the cache actually using physical addresses, right? It's not using virtual addresses, so the aliasing issues will not happen. Similarly, there will be no problem with context switch because you are doing the translation and accessing it using physical address, except that you are doing the translation in parallel. Okay, what is the disadvantage? The disadvantage is that if you have a direct mapped cache, the size of the direct mapped cache cannot be bigger than the size of the page. Why? Because only the page offset bits are being used to do the indexing and the block offset. So the number of blocks you have is limited by the number of bits in the page offset. Okay. So because of that, your direct map cache size is limited. What's the solution? Solution is that people use increased associativity at level 1. Why? Because by having increased associativity, without increasing the number of index bits, you can increase the number of blocks in your cache. Okay. So that is the solution. Therefore, today you hardly see any direct mapped caches at L1 also in because they do the virtually indexed physically tagged caches, and to prevent the size of the cache from being too small, they use increased associativity for that. Any questions? So data items difference with different variable names and hence different virtual addresses map to different physical addresses, right? But they should actually map to same physical location. What I mean, I think I shouldn't say physical map to different physical addresses. I should say map to different physical locations in the cache, but they should map to the same physical location. Okay. What's the solution? Some of the operating systems do something called page coloring, where what they do is so it's the operating system and the compiler together have to work very hard to achieve something to prevent aliasing if you're using virtual caches. Okay. What do? I'm actually, introducing this because some OSs use it, and I thought the book talks about it, so I thought I would like to cover it. So what we are seeing is that there are aliases. We are using virtual caches. So they have two different virtual addresses. And because we are using virtual caches, they can, fall into different blocks in the cache and therefore have non-uniform values. They should actually have the same value, but they can have different values because one gets updated and the other doesn't get updated. So what does the operating system do along with the compiler? They determine which are the aliases. Okay. They know what are the variables which are aliases of each other, and they generate virtual addresses such that they fall into the same block. That is, there is a conflict when you use aliased addresses. There is a conflict. So they'll actually fall into the same block. They cannot fall into different blocks. Therefore, the data will be basically sort of replaced. You can think of it as, the data is replaced. But so you will essentially, if you modify one location, it's like modifying the other location also, because they fall into the same block. And so the indexing and offset, just as we talked about, using the page offset to do this, in the virtual caches also, they are able to achieve this by ensuring that the virtual addresses of aliases are matching in the last few bits of their addresses, so that they'll actually, be in conflict with each other and are able to, avoid this problem. So one last thing about page coloring. When you're talking about virtual address allocation in, operating systems, it is possible that, you have these virtual addresses here, right? So you have your virtual addresses here and virtual addresses here. The thing is that if, contiguous virtual addresses may fall into non-contiguous physical addresses, right? Because think about what happens in your paging. You are basically saying, I have virtual addresses contiguously from 0 to some 4K if my executable is 4K. But your physical addresses may be split. Sorry, I shouldn't say 4K, because 4K is generally the page size. So let's say I have some 16K executable size. So I have 4 pages. So I have page 0, page 1, page 2, page 3 in my virtual address. When I map these 2 frames, I can get them in any frame, right? There need not be contiguous frames. In fact, the whole point of paging is we don't need contiguous allocation. Now, it is possible that when you map these virtual addresses to physical addresses, the physical addresses may actually conflict with each other, right? A contiguous virtual address, that is page 0 and page 1 of the virtual addresses, may be mapped to 2 frames such that they map into the same blocks in the cache. So if you want both page 0 and page 1 in your cache, it is going to be not possible, because they'll be kicking out each other and your miss rate will go up. It is basically thrashing at L1 level, right? You have read about thrashing in paging. This is thrashing at the caching level. Okay. So to prevent such things from happening, this is page coloring. Basically, contiguous virtual pages will be colored in certain fashion. The physical pages will also be colored, and you map the virtual pages to the frames according to their colors. You don't arbitrarily allocate frames to pages. So to avoid these sort of conflicts at the cache level. So some of the operating systems use these techniques, and not Linux. Okay. In fact, in the discussion forum related to memory hierarchy chapter, I'll be posting one very interesting exchange between some of the Linux developers, including the answer from Linus Torvalds, why he does not believe in page coloring in Linux. It's a very interesting thread, so I think you can read it up. And the most interesting thing for me is that you will certainly be able to understand what they are saying if you understand your OS and the architecture memory hierarchies that we have covered so far. So if you don't understand something there, you can always post in the forum. We can have a discussion. So in summary, right, of the basic cache optimizations, this basically is picked up from the Hennessy and Patterson book. Large block size reduces miss rate, but increases miss penalty. Okay, has no real effect on hit time. Large cache size increases hit time and reduces miss rate. Higher associativity increases hit time and reduces miss rate. So multi-level caches reduce miss penalty, have no effect on hit time and miss rate. Read priority overwrites reduces miss penalty, and avoiding address translation reduces hit time. Okay, so these are the various 6 optimizations that we talked about. In the next class onwards, we'll be talking about advanced optimizations, 10 of them. So I'll also be posting the video which covers a lot of what we have done and what we will be doing. So you can go over them probably over the weekend. They're very nice videos, very short videos. So let's see how it goes. Any questions you have, please raise in the discussion forum. I have been checking every day to see if there are any questions or anything. So I can answer there, and I'll post that thread of Linux people also, like I said. Anything else?
Ma'am,
Yeah.
could you go back to the right and miss slide?
Okay. Right through, huh?
Right through, yeah.
Okay. So the thing is something like this. You have a write through cache, right? But which is using a write buffer. Otherwise, if you don't use the write through buffer, it'll have to go to the main memory. Let's assume at this point, no multi-level cache. It's only, we are talking about a single cache between the processor and the main memory. Okay. So when you write it to that cache, it should go to the main memory also, because that is a very costly operation and it will block the cache. You will basically, put it into the write buffer and let it go through. Okay. Now, it is possible, though, it's probably quite a complicated set of reads that might lead to this, that after you do the write through, you have written to the write buffer, the block gets replaced.
Okay.
Okay, the block gets replaced. And so it gets replaced because you issued a read for something and there was a conflict, it got replaced. So you will issue the read will come through. You will use that, then you maybe again issue a read for the old value. Okay, which got replaced just now, right? Occasionally it can happen. That's, basically a bad conflict that is happening on the cache block. So when you reissue the read on the block you were trying to write through earlier, the write through may not have completed, right? So what is the sequence? You have a write through, it went into the write buffer. Then there was a read which replaced this block. Write is not completed to the main memory. And then you issue a second read, which again goes back to the old block. But that old block is not there. So it's a read miss. Now the updated value is not in the main memory because it's in the write buffer. It's not yet written back to the main memory. So if you read from the main memory, you're going to get the old value. You actually need to verify one of the two things you have to do. You have to wait for the write buffer to be empty because you don't know whether the value you're trying to access is part of the write buffer or not. So you wait until the write buffer is empty and then go and issue the read to the main memory. That will actually increase the miss penalty very much. So what do? You go and verify if the value you are trying to access is in the write buffer. If it is, use it directly from the write buffer and don't go to the main memory. So that is basically how you reduce the miss penalty in this case.
So if we consider multi-level cache,
yeah, if you consider multi-level caches and you are talking about exclusion,
okay,
then you will have such problems, right? Because you are going to go from L1 to a write buffer to the main memory.
yeah,
So this issue can come up. But when you're talking about inclusion also, yeah, when you talk about inclusion, most likely it'll do, in practical terms, to my knowledge, what they do is they do write through level 2 from level 1. Okay. Because the miss penalty is not that high. I mean, the number of clock cycles to access L2 will be about 10 cycles, say. Right?
okay,
So they do a write through from L1 cache and write back from L2 cache.
okay,
Generally. So inclusion will help, right? Because whenever you write to L1, you write through to L2. And let L2, if it is replaced, to do write back to main memory at some point. That's the general design.
okay.
Okay. Okay, so any further questions? That I covered a lot of stuff today. So if you can go through it, go through those small videos. I'm going to put up them like 58 videos. He also has exercises, very sweet, nice, small exercises, which allow you to understand this one. In fact, it doesn't go to the next video. I don't know how it will go. In Windows, maybe there is some way it will go. In Linux, it's just getting stuck for me. I have to reload the page and go to the solution page. So it's a very nice, this one, that they have put up. This is from Georgia Tech University. See, like I said in the last class, I have a problem when people use resources from the internet which are not from experts, because I'm very, very worried about whether they are telling the right thing or not. In fact, I'm worried about myself also. That's there. So I do a lot of research when I teach architecture. So anyway, I'm just cautioning you about using internet resources. In fact, I'm putting up resources which I think are really good from really good universities. So, okay. All right. Thanks for staying back beyond your time, and you must be hungry. So have a good weekend. Bye.
Thank you.
Thank you, ma'am.